Hey guys, this is Mr. Bennett and this is video 12-2. We're going to talk about the difference between evaporation and boiling. To understand that, we need to talk about two types of pressure first. We talked about pressure just the other day. We talked about the idea that think of pressure in terms of collisions, meaning when we're talking about any sort of pressure that involves a gas, it's the gas particles colliding with an object that creates the pressure. It's the collision, the force of the colliding. Okay, so there's two types of pressure that we need to consider. First is atmospheric pressure. So atmospheric pressure is the force of simultaneous collisions, because again, pressure is created by collisions, of rapidly moving air molecules. So that's the important thing. When we're talking about the atmosphere, we're talking about the air around us. So atmospheric pressure that's acting on me right now is created as the air molecules around me collide with my body. And we typically measure atmospheric pressure using a tool that we call a barometer. Okay, so if you've ever watched the weather and they're talking about barometric pressure, well, barometric pressure is basically they've taken a barometer and they've determined the atmospheric pressure. So it's really atmospheric that they're talking about. Now, here I have a picture of an atmosphere. So we've got the standard picture on the outside, and then in the middle, they've actually kind of created the little dots that represent the air particles. Okay, now to help you visualize what atmospheric pressure actually is, we're going to use this picture. So I'm going to zoom in, or zoom out a little bit. So if you look on the right hand side, it says up here the pressure is 0, and down here the pressure is 101 kPAs, kilopascals. Okay, so notice it's essentially increasing as we go down, as the altitude decreases. Okay, and that's because of gravity. Gravity is pulling down on air molecules, right? So they're going to tend to be pulled down towards the earth, hence there's more air molecules closer to what we call sea level. Okay, sea level. So we have more air molecules down here, and because closer to the ground you have more air molecules, that means you're going to have more collisions, right? Which means that you're going to have more pressure. Okay? So more air molecules means more pressure, and because gravity is forcing most of the air molecules down close to the ground, you have a higher pressure closer to the ground than you do up high. Now, the air molecules don't stay here. Remember, air molecules have the ability to expand and to go out in different directions. So even though gravity is pulling them down, some of them are flying back up, and that's why we do have some air up here. We just have less of it, hence we have less pressure. Okay? Now, atmospheric pressure, because of this, depends on altitude. Okay, temperature can affect it as well, but altitude plays a big role. So as it turns out, if we increase the altitude, we decrease the atmospheric pressure. We call this an inverse relationship, meaning they're opposite. So if I go up in altitude, atmospheric pressure goes down. Okay, AP just stands for atmospheric pressure. Okay, and again, sea level is where the ocean is. Okay. And so we define atmospheric pressure at sea level as being equal to 1 atmosphere or 101.3 kilopascals. These values are on the back of your periodic table in class. So you don't have to memorize these values as much as you just need to know where to find them and that they represent sea level. Okay. Now I said there's a second type of pressure we need to think of. The other pressure we need to think of is called vapor pressure. Vapor pressure is the force of the particles of a liquid that are changing into a gas phase. Another word that they like to use instead of changing is transitioning. Essentially the same idea. You have a liquid and it's turning into a gas. Okay, so here I have my flask, it's stoppered. We have water inside of it, and you can see that the water molecules are transitioning. The liquid molecules, we don't necessarily know it's water, right? But those liquid molecules are transitioning into a gas, right? So in order for them to do that, in order for them to break free of the liquid and to become a gas, they need to have enough kinetic energy. They need to be moving fast enough to become a gas, right? And then they also need to break intermolecular forces. Right? Another way of saying that is intermolecular attraction. They're attracted to each other. Attraction. Sorry. Didn't really fit there. But that word's attraction. Okay? So they have to break free of those attraction or those forces. Okay? And so if we put that all together, those two statements together, if we increase the kinetic energy, we are going to decrease the intermolecular forces or attractions, and that's going to raise our vapor pressure. Meaning we heat it up, we get more liquid turning into a gas, or if we break those intermolecular forces, we get more liquid turning into a gas. The more liquid we have turning into a gas, the more vapor pressure we have. Okay. Now, that means that there are really two factors that control the vapor pressure of a liquid. The first one is the temperature. So temperature plays a big role because temperature is tied to kinetic energy, right? So this is going to help determine that, right? And then it also depends on the liquid itself. So the liquid type. Okay, and I think I flipped these. It really should say vapor pressure depends on the type of liquid and the temperature, but you get the idea. So the reason why the type of liquid is important is because that's what determines your intermolecular forces. Water, as a molecule, has different properties than, say, alcohol. So they have different intermolecular forces. Water molecules interact with each other differently than alcohol molecules interact with each other. Okay, that's going to control how easy it is to transition it from a liquid to a gas. Okay, so rule of thumb, just in terms of temperature, is if you increase the temperature, you increase the vapor pressure because you're giving it more kinetic energy. All right, if you want something to evaporate fast, you generally alter the temperature. Okay, or if you want it to have more vapor pressure, I guess. All right, so now we've got two different types of pressure. Let's examine what's the difference between evaporation and boiling. Okay, evaporation, I think of it as like boiling, like it's before boiling. Like evaporation graduates to boiling. Okay, so evaporation is the transition of a liquid to a gas that occurs only at the surface of a liquid. So if I have a glass of water, the surface is evaporating. Okay, if it's just at like room temperature. That's why puddles evaporate. Your pool in your backyard slowly evaporates. Okay, but they're not boiling, right? Boiling happens when you have enough kinetic energy that the liquid is transitioning to a gas throughout the entire liquid. So that word is entire. So when I have something boiling, it's bubbling and it's frothing. And those bubbles in the boiling liquid are actually vapor of that substance. So if it's water boiling, it's water vapor that's inside those bubbles and it's transitioning into a gas. So the entire liquid throughout the entire sample is transitioning into a gas. Okay, so if we go back to evaporation for a second, the amount of evaporation is determined by the balance between, wait for it, atmospheric and vapor pressures, right? So that's why we needed to know these two guys. We need to understand those two, what they were, because it's the balance between those two that determines whether you're evaporating or boiling. Okay, so generally speaking, if you increase the vapor pressure, you increase the evaporation. Atmospheric pressure works the opposite. If you decrease atmospheric pressure, you increase evaporation. So notice vapor pressure and evaporation, we call this a direct relationship, meaning you increase one, you increase the other. Atmospheric pressure and evaporation, we call an inverse relationship because they're reverse, essentially. Okay, so if you decrease atmospheric pressure, you raise evaporation. Okay. Now, okay, so that's evaporation, but okay, how do you get to boiling? Well, boiling occurs when your vapor pressure is greater than your atmospheric pressure. Okay, so when this is bigger than this. Why? Well, let's take a look. I've got this little diagram down here. So it turns out if you have a sample of water, so here we've got my little glass of water, okay, we know that vapor pressure is basically the liquid trying to become a gas, right? And atmospheric pressure is really the air pushing down, right? So essentially what's happening here is the vapor, the liquid, is trying to turn into a gas. So it's pushing up, okay? And the air is pushing down, which is actually pushing these gas molecules back into a liquid, okay? So these guys are getting kind of pushed back and forth. Vapor is trying to make them a gas, and atmospheric pressure is trying to turn them back into a liquid. So it's kind of like a reverse tug of war, like they're pushing at each other instead of pulling, okay? And so if atmospheric pressure wins out, then it's really hard for these gas molecules to escape. So evaporation is happening. It's slowly turning into a gas. Okay? But if you crank up the vapor pressure, right, and this gets really, really big, it will overcome atmospheric pressure. Okay? And you'll get more evaporation. You'll get more of these gas particles escaping. Okay? Or basically more liquid turning into a gas. So boiling is when the vapor pressure overcomes the atmospheric pressure. So you have vapor pressure greater than atmospheric. Okay? Another way of thinking of it is vapor pressure is trying to turn the liquid into a gas. Atmospheric pressure is preventing it or resisting the change. Okay, so if you decrease the resistance, evaporation increases. If you increase the resistance, evaporation slows. So it turns out, because of that, there are two ways that you can actually get a liquid to boil. The first way is you can raise the vapor pressure by increasing the temperature. Right? We know if we heat up a sample of water, then particles are going to move faster. They're going to have more energy, so they can escape as a gas. Right? So vapor pressure will increase and eventually overcome atmospheric pressure. The other way to do it is decrease the resistance. So if you want a sample to boil, you decrease the atmospheric pressure. That way there's less resistance, right? So the vapor pressure can essentially do its job, and evaporation will increase as you decrease this resistance. Okay, so to kind of sum things up, give you a little example here. We said earlier that atmospheric pressure decreases as altitude increases. So as you go up a mountain, right? As you go up the mountain, your atmospheric pressure is going to decrease, right? That means that as you get up to the top of the mountain, you're going to need less vapor pressure to get it to boil. Because remember, for boiling, vapor pressure needs to be greater than atmospheric pressure. So if your atmospheric pressure has decreased, you won't need as much vapor pressure to get it to boil. And what that means is boiling points actually decrease. Keeps doing that. Boiling points actually decrease as altitude increases. Okay? So what does that mean? Well, that means that we can actually, there's different boiling points for water depending on the altitude that you're at. So as I go up this mountain, water's boiling point will actually decrease. Turns out at sea level, water boils at 100 degrees Celsius. Okay? We call that water's normal boiling point. Okay? So it's when the vapor pressure needs to be greater than 1 atmosphere, because 1 atmosphere is the atmospheric pressure at sea level. Okay? So if vapor pressure needs to be greater than it to get it to boil, it means it needs to be greater than 1 atmosphere. Okay? And that's the normal boiling point for any liquid. Normal boiling point is defined as being at sea level. Okay? Which means that the vapor pressure of that liquid needs to be greater than 1 atmosphere. All right? Make sure that you complete your WISC questions, and we'll see you tomorrow.